Hello and welcome to this manufacturing process technology part 2 module 28. I was talking about the basic electro discharge machining process when I was further discussing about how spark is generated in a medium because of a discharge of electrons, and then how it creates an ion column, it creates ionization and secondary electrons, and then how those electrons actually are responsible for removal of material similar to the ions. And electrons remove more material in comparison to the ions because there are more in numbers and also are able to transfer more amount of momentum to the surface in which they go and strike, and so the anode is normally made the tool. Also further we kind of discussed how the spark would be generated all over the surface depending on what is going to be the nearest distance between the crevice or the peak on the tool surface with respect to the workpiece surface. So in line with that, what we learned is that the spark produces a compression shock wave, okay, which results in the development of a very high temperature near the region hit by the spark, and this melts and vaporizes the anodic material. The melted vapors are further removed by the mechanical blast, and obviously there is also going to be an electron pressure, and this results in a sort of a pitting on the electrode surface. So the temperature in the melting zone is roughly in the range of about 10,000 to 12,000 degrees Celsius. The dielectric fluid or the dielectric oil has a flash point, but then it is so momentary and so small that it is not able to generate, and there is also a quick dissipation of the heat which is generated or accumulated, and so this hot spot that is generated may not be enough to create a chain reaction and in general an ignition of the whole oil. So this results in small craters in both the electrode surfaces. A number of craters created on the anode surface is of course more than the cathode surface, and as soon as this happens, the gap between the electrode at A increases, and the next location is the shortest gap is somewhere else, say B. For example, let us say A was the one where the gap was smallest, there was a spark because of which there is a melt, and this gap has now increased, and maybe some other place B has the smallest gap where there would be a breakdown again, because obviously you have to remember that the E breakdown has to be arrived at, and the voltage here E should be at least greater than the Z breakdown, which is actually a function of the voltage applied and the inter-electrode distance. So the D is varying quite a bit between, let us say, D at A or D at B or maybe D at C, okay, and so therefore whatever creates this condition first as the first part. So it is in a way as described above, that the spark wanders all over the electrode surface. It is like a dancing spark. So if you see an EDM machine, you will find that the sparks which are created are not at one place, but at several places along the tool electrode surface, and they keep on changing orientation randomly, and you do not know at what place the spark would get generated, and ultimately the process results in a uniform gap over the whole surface. So EDM also in a way can be treated as more or less a die sinking process. So having said that, let us learn a little bit about the mechanics of the EDM process. So the first important aspect here is that a negative of the electrode shape is created, okay. I just told you in the last step how it is a die sinking process, and generally the rate of material removal from the cathode is comparatively lesser than that from the anode, and more because of two reasons. I think I have pointed it out in summary. The momentum is one of the reasons. The momentum with which the stream of electrons strike the anode is much more than that due to the stream of the positive ions impinging on the cathode. Though the mass of an individual electron is less, but the number density of the electrons are simply humongous in comparison to the ones created in the column in forms of positive ions. Also there is a tendency of some kind of a breakdown of the EDM oil or the dielectric medium which is there between the electrode. We call this breakdown process pyrolysis, and because the dielectric fluid is normally a hydrocarbon, pyrolysis of such hydrocarbons create very thin films of carbon deposits, particularly on the cathode, because obviously there are ions moving or created through this pyrolysis process in the medium, which would be going to ultimately deposit at on the anode surface or on the cathode surface, and that too with high amount of momentum, where the local temperature may reach to a level where it may burn down the hydrocarbon and produce only carbon deposit. So, slowly you will see the tool surface being covered with carbon as the process continues, and the compressive force that is developed on the cathode surface is primarily because of the cations, and it is a normal strategy that the tool is connected to the cathode side of the DC terminal or the DC source in a EDM process. So, that is about the mechanics of the EDM process. Also, if the tool is stationary relative to the workpiece, the gap increases as the material removal progresses, and if you do not close on the gap through servo control or some other mechanism, obviously there will not be any sparking action anymore. So, if the voltage is not increased, so either you need to increase the voltage in case the gap increases, or you need to change the gap in order to have a sustained initiation of sparks across the medium between the two electrodes. So, the tool feed is the common strategy which is used for closing on the gap as the gap gets enhanced because of this process of material removal. And so, typically a servo drive which senses the gap voltage and determines by a comparative with the preset voltage keeps the gap more or less constant, so that the sparking process can be sustained. Let us look at some understanding of how to generate the material removal rate values in a EDM process. Okay. So, the quantity of material which is removed due to a single discharge can be determined, and then you could do something with multiplying that with the spark frequency, so that you have an idea of per unit time how much such material can be removed, and you can also have an idea of how one spark would be able to, in terms of volumes of material removed, contribute. So, such volume times the spark frequency or the frequency at which this volume gets depleted would give you an idea of the overall material removal rate. So, we have to first look at the quantity of the material, which will be determined by considering a sort of a crater being formulated with a fixed diameter and depth up to which the melting temperature is reached, and this is a very important point in EDM which we better know as depth of melting temperature. So, obviously, it is very clear that wherever the temperature of the material is above the melting point, those are really the areas which get molten, or above or equal to the melting point, I should say. Those are the areas which get molten, and for the temperature distribution to reach up to that point, you also need to study how the temperature varies with respect to depth, and obviously at a certain depth from the surface or up to a certain depth of this of the surface where the spark has hit, the condition of temperature greater than the melting temperature or equal to the melting temperature would exist. So, typically that is the zone which would give you how much melt is formulated, and that is the zone which would be needed for estimation of the overall diameter of the crater and the depth of the crater. So, we make some assumptions for making the model simpler and for modeling the temperature in the zone of spark. The first assumption we make is that the spark is a uniform circular heat source on the electrode surface, and the circular heat source has a diameter of 2a. So, this is mostly looking at the number of pits which are formulated after the EDM process under microscope. We could get a fairly good idea of what is going to be the overall diameter of such a heat source. So, the diameter of the circular source remains constant, and the electrode surface is again a semi-infinite region. This is more so because we want a distribution only in the radial direction and not as a function of the angle theta. So, except for the portion of the heat source, the electrode surface is considered to be insulated, and there should not be any other heat inflow except what is coming from a spark. Obviously, the rate of heat input remains constant, that is what another assumption is of this model, and that should be throughout the discharge duration, although this is really something that can be modified quite a bit, because a discharge really although it is a momentary affair, but when we talk about micro machining particularly, there may be a finite time duration of the discharge, and the volume of material that is being removed there is very small. Okay, so, that finite time of discharge may be played around with very easily to obtain, at least for finishing processes, a very good estimation. Okay. So, here for all practical purposes, we would assume the time to be so small, time of discharge to be so small, and the machining overall time to be so huge, that the discharge can be treated as more or less a momentary affair. And the properties of the electrode materials further do not change with temperature. So, we do not assume any kind of thermal expansivity or any kind of change in conductance because of a change in the temperature. And also we further assume that there is no vaporization, the only route to material removal is through melting and removal of the material through diffusion into the the dielectric fluid. So, the vaporization of the electrode material is more or less neglected in our theoretical estimation of the MRR. So, let us now look at the underlying governing equations for solving this radial and Z based or depth based distribution of the temperature. So, let us assume theta to be the temperature of a certain point within the material in degrees Celsius. Let us also assume time t in seconds, okay, to be a parameter which is responsible and contributive of the variation of the temperature theta. We also assume some standard K value, thermal conductivity value. As per our assumptions made earlier, we do not assume this conductivity to change based on temperature increase or enhancements. So, this can be a constant, calorie per centimeter second degree Celsius. There is also a constant thermal diffusivity that we assume. Units of thermal diffusivity in this case can be centimeter square per second. We can further assume a discharge time of Td in seconds. And this could be more like a duration over which the spark hits the anode. We assume a certain melting temperature of the material, let us say theta m. This is the melting temperature of the material. This can be in degrees Celsius. And further we have H as the total heat input out of a circular spark, and this can be mentioned in calories. So, having assumed all these parameters, let us now formulate the heat conduction equation. Particularly for the cylindrical geometry that we are considering, including the z direction, the radial distribution, and also the distribution with respect to theta, where because we have assumed an infinite boundary condition there, the difference because of the theta angle really does not matter, it is all about the radius and the depth z. So, we formulate the heat conduction equation for cylindrical geometry assuming no variation with angle phi. Or we can call this circular symmetry. So, we can write this equation as del theta by del T equals thermal diffusivity alpha times of del 2 theta by del R2, R being the radius. Let us just write it here, R is the radius of the circular spot, which in this case is A, the diameter is 2A, diameter of spot or spot size. So, del 2 theta by del R2 plus 1 by R del theta by del R plus del 2 theta by del Z2 equals del theta by del T. So, that is how the equations are, the governing equation is represented for this circular geometry, and intuitively it can be, so intuitively it can be seen that the depth to which the melting temperature is reached is maximum at the center of the spot, and really we have to evaluate the solution at r equal to 0 or at the center. So, this will give us the maximum depth of melting temperature. So, if this is the radius A, we are talking about a crater where this Z, which corresponds to the boundary condition theta greater than or equal to theta melting. Okay. So, this Z formulated on the basis of this boundary or this theta equal to theta melting boundary is obviously going to be maximum corresponding to r equal to 0, and it is going to be 0 at r equal to A. Okay. So, let us now evaluate the equation at r equal to 0 with certain boundary conditions. We have 3 different boundary conditions we will be using in this case. One is the constant rate heat input, one is the uniform heat flux, another is the circular heat source. So, if we write the boundary conditions mathematically, we assume that the first condition can be that at all values of t is equal to 0 or less than 0, the temperature as a function of r, z and t is same as 0. We consider this to be the room temperature. So, we are having a temperature differential with respect to the room temperature in a scale, and so therefore, theta is equal to 0. Okay. And we further assume that corresponding to any time values greater than 0 and radius greater than A, there is no temperature gradient which exists, or del theta by del z is equal to 0 in the z direction outside the spot or outside the radius. So, there is no temperature gradient along the z direction, and inside the radius, let us say between values of r between 0 and A, we do have a sort of a constant heat flux boundary condition here, where we say that minus k d theta by dz equals to the heat per unit area per unit time. Okay. So, this is the power per unit area. So, we can say that H is the amount of heat energy in calories, and we can say the heat per unit area per unit time for the discharge duration Td. Okay. So, we assume a step function as far as the rate of heat input goes with respect to time. This duration here is the whole sparking duration, and there is a uniform heat flux while the spark is operating. So, this is a quite a bit of simplification. So, this is pi a square Td. So, these are the 3 boundary conditions that can be used to evaluate the governing equation that has been written in the section here, and the equation can be solved by variable separation or some other technique. Assuming no variation in theta or no variation in phi, or assuming circular symmetry, and corresponding to the spark center are equal to 0, we have the theta at 0 z T d equals half h pi k times of a times of T d integral 0 to infinity Bessel function of dummy variable zeta a of index 0 times of the first Bessel function of zeta a times of e to the power of minus zeta square times of the error function of second kind of the term z by twice root of alpha T d minus zeta root of alpha T d d zeta by deta. Zeta is the variable of the integration here. And out of the solution, if we wanted to find out z, which is the depth up to the melting layer, we get a more simplistic equation. Theta m equals twice h root of alpha T d by pi k square T d times of the error function of the third kind z by twice root of alpha T d minus error function the third kind root of z square plus a square by twice root of alpha T d, where I would just like to write these different notations on different formulations of the different error functions. So, the I ERFC zeta can be written down as 1 by pi e to the power of minus zeta square minus zeta ERFC zeta, and the ERFC zeta can further be written down as 1 minus the error function of zeta. And as you all know, the error function of zeta is a numerical integral given by twice root of pi 0 to zeta e to the power of minus x square dx. Okay. So, this is A, B and C. So, this expression right here is merely representational, but it gives you a condition where the theta or the temperature is actually equal to the melting temperature or greater than the melting temperature. So, and this can be a very good iterative means of estimating what is going to be a value of the zeta for a corresponding value of radius. Okay. So, this a can vary between anywhere between 0 and a, for example, and it could give you an estimate of where are those points where the theta really is within the ambit of, or it is more than or equal to the melting temperature. So, I think I would like to stop here and maybe take this up a little further and maybe try to do something so that we can have a prediction of the Z value through which we can actually have a crater volume estimation. I did not intentionally solve this the solution of these equations because we just want to utilize what is the final solution in terms of the variation of theta with respect to Z and the radius. And however, if there is a query on how we arrived at this process, a detailed notes probably can be shared over the chat platform later with you guys. So, with this I would like to stop this particular module, and the next module we will try to estimate the material removal rate from the Z value that we obtain corresponding to different values of R, okay, where the theta equals theta m, and then estimate the volume and then multiply with the spark frequency in order to get a theoretical estimation, a ballpark value of what is going to be the MRR. So, with this I would like to stop this particular module. Thank you very much for being with me. Thank you.